Let's solve Unit 2 Computer System Architecture questions. Match the list 1 with list 2. We are given Boolean algebra law in list 1 and the axioms in list 2. Let's start with absorption law. Absorption law, A will be mapping to 4. A plus A into B is equal to A. A4 is available in 2 of the options. We can rule out the other 2. What about bounded law? If you are new to this term, you can directly move to distributive law to find the answer. Distributive law, D will be mapping to 3. A into B plus C is equal to A into B plus A into C. D3 is available only in one option, so we can even rule out this one. So based on A and D's answer, we can conclude option number 1 to be the right answer. What about identity law? C will be mapping to 2. A plus 0 is equal to A. What about bounded law then? A plus 1 is equal to 1. B will be mapping to 1. So we have A4, B1, C2 and D3 as the right answer. Next question. Consider a pipeline unit for fixed point multiplication of 8-bit integers. Arrange the following stages in a correct sequence. Let's take that we don't have any idea about pipeline unit for fixed point multiplication. Without any idea, how are we going to solve this question? Let's read the stages. Stage A consists of 2 CSAs and it merges 4 numbers from previous stage. Based on this particular clue, previous stage, we know this particular sequence will not start from A. So we can rule out option 4. What about stage B? Is a CPA which adds up the 2 numbers. From here we can understand that it is going to be a continuation of some stage. The option starting with B will also be ruled out. What about C? Is made up to 2 level of 4 CSAs. Again, this is a continuation statement. So we can even rule out option 1 that is starting with C. Now the only option that is left is option 2. Stage D generates 8 partial products. This is the only stage that feels like the beginning of the sequence. And we have only one option that is starting with D. So just based on this you can mark option 2 to be the right answer. You can use this particular approach when you don't have any idea about the topic from which the question is asked. Now we will get into the learning. Let's consider an example. The multiplication of two 8-bit integers A and B. So they have given 8-bit integers multiplication. So we are picking two 8-bit integers here. A into B is equal to P, where P is the 16-bit product. This fixed point multiplication can be written as the summation of 8 partial products as shown below. P is equal to A into B can be expressed in 8 partial products along with summation. So this will be P0 plus P1 plus P2 plus P3 plus P4 plus P5 plus P6 plus P7. So there are 8 partial products where this symbol is arithmetic multiply and this symbol is add operation respectively they have given. Now let's see about the stages. This is the exact diagram that we can find in Advanced Computer Architecture book. So this is A and this is B. We have two 8-bit integers here. The first stage generates all 8 partial products ranging from 8 bits to 15 bits simultaneously. So here it is the number of bits. So again we have 8, 9, 10, 11, 12, 13, 14, 15 bits. This is what they have given as ranging from 8 bit to 15 bit. This is S1 stage and here we can equate it to generates 8 partial products which is D. After that we have the second stage. The second stage S2 is made up of 2 levels of 4 CSAs and it essentially merges 8 numbers into 4 numbers. So this is level 1 and this is level 2. How many CSAs are there? There are 4 CSAs. 1, 2, 3, 4. This is stage 2. Which stage is having the same statement here? Is made up to 2 level of 4 CSAs. This is the clue that we can get from this particular statement. So the next stage will be stage C here. What about the third stage? S3 consists of 2 CSAs and it merges 4 numbers from S1 into two 16-bit numbers. So how many CSAs are present? 2 CSAs, that's what is given here, and they say it merges 4 numbers from S1. S1 is nothing but the previous stage. So here this can be equated to consists of 2 CSAs and it merges 4 numbers from previous stage. This previous stage is what is denoted by S1 in this particular statement. So the next stage will be A. What about S4 stage? The final stage is a CPA which adds up the last two numbers to produce the final product P. This is a CPA which adds up the two numbers is what they have given in stage B. This will be the final stage. DCAB is available in option number 2. So we go with option number 2 as the right answer. Now we have come across two terms, CSA which is carry save adder and CPA which is carry propagate adder. What are they? High speed addition requires either the use of a carry propagation adder CPA which adds two numbers and produces an arithmetic sum, or the use of a carry save adder CSA to add three input numbers and produce one sum output and a carry output. So in stage 2 and stage 3 we are going with CSA, and in the final stage we are going with CPA. If you get to learn about CPA and CSA, they will tell you how this bit by bit addition is performed and where the carry goes, everything. So I am not including those details here, but if you want to extend your learning about CSA and CPA, you can refer to Advanced Computer Architecture books. Next question. Arrange the following in the increasing order with respect to access time. So let's see a diagram now. We have 5 levels here. Registers in CPU, cache which is denoted by SRAMs, static memory. Then we have main memory, the dynamic RAM, the disk storage which includes solid state and magnetic drives. Regarding the last level, we have backup storage which includes magnetic tapes and optical disks. They have given increase in cost per bit from bottom to top in this side, but here it is given as increase in capacity and access time from top to bottom. So if something is going to be accessed in 0.1 second here, this will take around 5 to 10 seconds here. So you have to arrange from top to bottom to get the increasing order with respect to access time. Increasing means from small count to large count. Ascending order we can take. So we will arrange this. First we have registers in CPU. It is available in option E here. What about SRAM? It is D. What about DRAM? It is C. What about disk storage? Here we are referring to solid state drive. So this will be A. What about optical disk? It is B. EDCAB is available in option number 4. Option 4 will be the right answer. Regarding these 4 options that is given for this question, once you find registers are going to take the least access time, you can answer this question without worrying about SRAM and DRAM. Next question. Which table for a dynamic pipeline become more interesting when a non-linear pattern is followed? In previous year questions, we have solved about pipelining and we have non-pipeline too. What is this dynamic pipelining? This is actually called as non-linear pipelining. This can be reconfigured to perform variable functions at different times. The traditional linear pipelines are static pipelines because they are used to perform fixed functions. You must have seen this diagram even in the solution videos. There will be 5-stage pipeline. All the stage will be going in a linear way for every instruction like fetch, execute, etc. So that is linear pipeline and they are called static pipelines. When there is no linearity, we can term it as non-linear pipelining or dynamic pipelining. Actually, dynamic pipelining is the right word. Some authors use non-linear pipelining, so I have mentioned even that term here. A dynamic pipeline allows feed forward and feedback connections in addition to the streamline connections. In linear pipelining, the stage will be moving on forward, but here you even have feedback connections. So you can see this diagram. This is a three-stage pipeline. So this is moving forward. At the same time, it is just moving backward also. Out of these four options, reservation table is associated with dynamic pipelining. The reservation table for a static linear pipeline is trivial in the sense that data flow follows a linear streamline. Trivial in the sense it is of not much importance. Why they say it is not important? Because when you take linearity, it is going to go in the same flow. There is no alteration. So there is no use of looking for the reservation table. But when there is non-linear approach, reservation table will have significant role there. The reservation table for a dynamic pipeline becomes more interesting because a non-linear pattern is followed. Given a pipeline configuration, multiple reservation tables can be generated for the evaluation of different functions. There is a possibility to have more than one reservation table in dynamic pipelining. So you can see this diagram here. One reservation table for a particular function x and the other reservation table for another function y. From this we can conclude option number 1 to be the right answer. Reservation table becomes more interesting because a non-linear pattern is followed. The exact statement is actually asked in the question. Next question, which are often needed to evaluate the cache performance? Let's see about the options first. What is hit ratio? The proportion of memory accesses that are successfully served by the cache memory. What about latency? It measures the time it takes to retrieve data from the cache. What about cache traces? This is a term that is helpful in analyzing and understanding memory access patterns. And what about transfer rate? Evaluates the speed at which data is transferred to and from the cache. In general, if you take about hit ratio, this provides a clear indication of how effectively the cache is serving memory accesses. A high hit ratio means the cache is frequently used, reducing the need to access slower main memory. So keeping this particular point in mind and the previous knowledge that we have about hit ratio, we can go with option number 1, hit ratio, as the right answer. But before providing hit ratio in the final answer key, the third option, cache traces, was given as the key in the provisional answer key. Where did this confusion actually occur? Some of the questions for this particular session is actually taken from Advanced Computer Architecture book written by K. Wang. In that book, we have certain statements. Due to the difference between page allocation in main memory and block allocation in the cache hit ratio and memory page hit ratio are affected by replacement policies differently. Cache traces are often needed to evaluate the cache performance. This was the statement that is actually asked in the question. This is the reason behind provisional answer key cache traces. But what is actually cache trace? They have given like this content will be discussed in a later chapter. But when you get inside the later chapter, you cannot find the term cache traces. What they have talked is the performance of a cache design concerns two related aspects, the cycle count and hit ratio. The cycle count refers to the number of basic machine cycles needed for cache access, update and coherence control. And the next one, the hit ratio, determines how effectively the cache can reduce the overall memory access time. So they have given this content will be discussed later, and in the later part of the book, these two terms were mentioned. So the right answer will be hit ratio and not cache traces. So I am just giving you clarification of why cache traces cannot be the answer. Next question. Which of the following is the simplified form of the given function? F of a comma b comma c is equal to summation of min terms 0 comma 1 comma 3 comma 7. So in 4 positions we have to place 1. Let's take the K map here. So we can take this to be A and this to be BC. This will be A dash, this will be A. Here it is B dash, C dash, B dash, C, B, C, B, C dash. What are the places where we should place 1? 0, 1, 3, 7. Now we have to do grouping. So we can group these two ones and these two ones. So what is common with respect to these two cells? A dash is common and we can take B dash here. So A dash B dash will be coming for this particular grouping. Now we'll get into this grouping. What is common here? We have BC common here. So the simplified format will be A dash B dash plus BC. This is available in option number 3. Option 3 will be the right answer. Next question. Which of the following is the complement of the Boolean function? We are going to apply complement to the complete function here. Before that, we will understand what is a complement. The complement of a Boolean function is obtained by flipping all the values of the function from 1 to 0 and from 0 to 1. Now let's find the complement of this particular function. Let's take f is equal to a dash b cd dash a dash b plus cd dash. Now you have a repetition of term here and similarly repetition of the other term. When you are going to have 1 plus 1, that will give you 1. When you are going to have 0 plus 0, that will give you 0. So we can simplify this and make it as f is equal to a dash b plus cd dash. Now we will find the complement of this particular Boolean function. It is denoted by f dash. We have to apply complement to the whole expression. A dash b plus cd dash the whole dash or the whole complement. We will take a dash b separately and apply this complement. Then we will apply for cd dash the whole complement. Now this particular complement of addition will become multiplication. So this is dot. Now apply the complement to individual variables here. So this will be a double dash. Instead of this dot, we can go with plus, and this will be b dash after applying complement. We will have the braces here. This will be into c dash plus d double dash. So how can we write a double dash? A complement to the complement will be a only. So this will be a plus b dash into c dash plus d. This particular expression is available in option number 3. Option number 3 will be the right answer. Next question. Correct the order of instruction cycle. So let's see the sequence here. In the basic computer, each instruction cycle consists of the following phases. Fetch an instruction from memory. So we can equate this to fetch the information in B. So this will be B. Decode the instruction. It is given in D. Read the effective address from memory if the instruction has an indirect address. So we can go with A. Read the effective address. Execute the instruction will be C. B, D, A, C is available in option number 2. Option 2 will be the right answer. Next question. Which of the following is the correct sequence with regard to service routine? So this question was earlier asked in one of the question paper. So let's see the sequence. The service routine must have instructions to perform the following tasks. Save contents of processor registers. This is available in A. Check which flag is set. This is D. Service the device whose flag is set. This will be C. Restore contents of processor registers. This will be E. Turn the interrupt facility on will be B. Return to the running program is the final task here. A, D, C, E, B. It is available in option number 4. Option 4 will be the right answer. Next question. Which of the following are not data manipulation instructions? Data manipulation instructions perform operations on data and provide the computational capabilities for the computer. The data manipulation instructions are usually divided into 3 basic types: arithmetic instructions, logical and bit manipulation instructions, and shift instructions. So let's see about all these instructions separately. In arithmetic, we have increment, decrement, add, subtract, multiply, divide, add with carry, subtract with borrow, negate, that is 2's complement. What about logical and bit manipulation? Clear, complement, and or, exclusive or, clear carry, set carry, complement carry, enable interrupt, disable interrupt. What about shift instruction? Logical shift right, logical shift left, arithmetic shift right, arithmetic shift left, rotate right, rotate left, rotate right through carry, rotate left through carry. Any instructions that fall under these three categories will alone be taken as data manipulation instructions. Do we have call anywhere? No. Do we have loud anywhere? No. Do we have and? Yes, it is available in logical. So this one is logical. What about increment? It is available in arithmetic. So this is arithmetic. What about shift? Though they have not mentioned what kind of shift it is, they have given it as an instruction. So shift is definitely an instruction because we have arithmetic, logical and shift instructions. So we can take the third point as it is. So this is shift. So C, D, E are data manipulation instructions. From here we can understand A and B are not data manipulation instructions. So we can go with option number 2, A and B only as the right answer. Now let's see about program control instructions. Here we have branch, jump, skip, call, return, compare by subtraction, test by ANDing. So here we have call. This call is nothing but program control instruction. Next question. Which of the following do not represent memory reference instruction? We have basic computer instruction formats. There are three kinds actually: memory reference instruction, register reference instruction, input-output instruction. Here this question is with respect to memory reference instruction. So what is this mode and opcode? Mode bit indicates the addressing mode. If mode is equal to 0, it means it is direct addressing. If mode is equal to 1, this can indicate indirect addressing or other modes. Opcode specifies the operation to be performed. So when you have a fixed mode of 0 and the opcode to be 111, all these instructions fall under register reference instruction. When you have I is equal to 1, that is the mode is equal to 1, which is indirect addressing, and the opcode to be 111, they fall under input output instruction. You have mode 0 opcode 111, mode 1 opcode is equal to 111 in option B and C. So based on this we can mark option number 1 to be the right answer. But the official answer is given as B and D. Just check with the memory reference instruction that is given here. We have 1, 2, 3, 4, 5, 6, 7 instructions ranging from 0 to 6. So you can see the opcode is equal to 000 through 110. So the values can be 000, 001, 010, 011, then 100, 101, 110. Once you have opcode is equal to 111, they don't come under memory reference instruction. Opcode is equal to 111 is often used for non-memory reference that do not involve memory access is what we can understand from this. They have asked which do not represent, that's why we are picking B and C, which means A, D, E are a part of memory reference instructions. If you take opcode in A, it is 010 which is available here, 110 it is available here, 001 is available here. This I mode can be either 0 or 1. That's why they have mentioned it as I directly. They have not given a value as 0 or 1. That happened in register reference and input output. Next question. Match the list 1 with list 2. Let's start with A. We have a binary number 100 110011. Base 2 means it is in binary form. And in list 2, we have a number in hexadecimal. To convert binary to hexadecimal, you have to group the digits by 4. These 4 should be grouped together. These 4 should be grouped together. You can even prepend zeros here and bring this to 4 terms. What is 0011? Just go for 8421 code. 0011 will give you 3. So this is 3. 0011 is again 3. What about 1? When you have 000 and 1, this is equal to 1. So this will be 1. You have 133 to the base 16 because you are converting it to hexadecimal. There is a series in this channel, CS Connect series. Here you have a playlist called Number Systems. In that playlist you have base conversions video. So in that video you can learn about the conversions between decimal, binary, octal and hexadecimal numbers. A will be mapping to 4. A4 is available in 3 of the options. So we can rule out 4. What about complements? Actually, what is the purpose of introducing the concept of complement is, it is to represent negative number. So we can map B to 3. A4, B3 is available only in one option. We can rule out the other two and we can mark option number 2 to be the right answer. What about C parity bits? When you take digital logic content, when they introduce parity bit, it is for error detection purpose. So parity bit is about error detection code. C is mapping to 1. What about variable length instruction? This is actually associated with CISC instruction set. D is mapping to 2. With this we are completing Unit 2 solutions.